Hi, and welcome to H2.2 Rigid Objects in Equilibrium. In this lesson, students will be able to create and analyze free body diagrams of rigid objects with torques applied to them so that they are in static equilibrium. All right, we've seen free body diagrams before in this class. They're going to be even more important now. So, equilibrium of a rigid body. A rigid body is in equilibrium if it has zero translational acceleration and zero angular acceleration. It's not accelerating linearly, and there's no angular acceleration. All the forces and the torques are balanced. In equilibrium, the sum of the externally applied forces is zero, and the sum of the applied torques is zero. So, and watch these. Do you see what I'm going to do with these animations here? The net force in the x direction is zero. The net force in the y direction is zero. And the net torque is zero. And I got points off because I didn't put newtons. And this is a Newton meter. Okay, very nice. So let's get right into an example because we've already seen how to deal with these net force equations. We've already seen how to make free body diagrams. We're just adding in torques to the equation as well. So a woman whose weight is 530 newtons is poised at the right end of a diving board with a length of 3.9 meters. The board has negligible weight and is bolted down at the left end while being supported 1.4 meters away by a fulcrum. Find the forces FB, that's like the force of the bolt, and FF, the force of the fulcrum, respectively, that is exerted on the board. Okay, so there's a force here somewhere and a force here somewhere, but I want you to think, what direction are those forces? Like, we know this person's weight is acting straight down. Okay, if you had to draw the direction of the force of the fulcrum, FF, how would you draw that vector? And if you had to exert a force that the bolt is like holding the diving board in place, what direction would you draw that force? But before we do that, let's use a problem-solving strategy to tackle this problem. So this is a great problem-solving strategy for rigid objects in equilibrium. Step number 1, select the object to which the equations of equilibrium are to be applied. So think to the previous problem, what is the object that you would apply these equations of equilibrium to? I would probably say the diving board itself, not the bolt or the fulcrum or the person, but the board. That's the thing that all the forces are acting on, the diving board itself. Step number 2, draw a free body diagram that shows all the external forces acting on the object. Step number 3, choose a convenient set of x and y axes and resolve all forces into components that lie along these axes. Think inclined plane, where we had the x-axis, we rotated it to be aligned with the plane itself, and the y-axis was perpendicular to it. And we did that because it was convenient. We had to resolve the vectors into less components. You just want to make something that's easier for you to analyze. Step number 4 says apply the equations that specify the balance of forces at equilibrium. The net force of the x and the y direction are in 0 because, again, we're in equilibrium. They're not equal to MA yet. Okay, so that's all well and good. We've done that before, but now we're going to add another step here for torques and rotation. It says select a convenient axis of rotation. Since your angular acceleration isn't changing at all, you could pick that axis anywhere. It says the choice is arbitrary when the object is in equilibrium. You're not actually rotating, it's in equilibrium. So it says identify the point where each external force acts on the object and calculate the torque produced by each force about the chosen axis. Set the sum of the torques equal to 0, just like we did before with these other equations. So we're going to have 3 equations now to help solve for our unknown. And by selecting a convenient axis, maybe there'll be 2 unknowns, and we'll put the axis where one of those forces is acting. Because remember, in the previous lesson, we said if the line of action is pointing towards the axis, there's not going to be a torque produced because the lever arm is 0. So by choosing the axis uh, aligned with one of your unknown forces, let's say this is, we don't know what this is, and we also don't know what this other force is, all right, then this one goes out of this equation because the torque produced by this is 0. That's like in a nutshell, in case you were wondering what the convenient axis is all about. But I'll show you in the example we're about to do. Step 6 says solve the equations in step 4 and 5 for the desired unknown quantities. So now you have 3 equations. Hopefully you only have like 1 or 2 unknowns, and you'll be able to figure out what to do from there. So if you'd like, you can try this example on your own. Didn't try it yet? Maybe pause the video here because I have the steps all laid out for you. What's the step number 1? All right, it says select the object to which the equation, okay, so we said before we're gonna do the board. And then step 2 is we're gonna draw the free body diagram for the board. So I'll do it here. If you didn't do it yet, that's fine. I'm gonna draw the board kind of large because what we're gonna end up doing is drawing in the lever arms. There's like a lot of distances and all the forces are at different points, and you got to try to figure out what that lever arm is. So the bigger it is, the better, because you got plenty of room on your page, and try to draw straight lines. So let's draw this free body diagram. That's the diving board, and you can kind of try to go left to right, or maybe we'll go right to left because this is definitely an easy one to draw. We said the weight definitely acts straight down. So we have this force here is, and you could call it FG. Let's call it W. W for the weight. That's what your textbook does, so we'll just do that. Then we have the fulcrum. What direction is the force that the fulcrum is exerting? All right, what direction is that fulcrum exerting the force? I would say it's like supporting the diving board. It's keeping the whole thing from falling downward. So the fulcrum is pointing straight up. So we have FF for the force of the fulcrum, not the force of friction. You could call it F1 and F2 if you want to. All right, totally up to you. And then what direction is the force that the bolt is here? Right? The bolt is like bolting this thing to the ground. What would happen if the bolt wasn't there? This whole thing would tip over this way, right? Because of this person's weight. So this bolt must be exerting a force this way to keep the board from moving that way, right? The bolt is exerting a force straight downward, and it looks like it's right at the end. It says at the left end. So we could draw that right at the left end. All right, and we could call that FB. Great. Now, as promised, we got to try to draw in some distances here. Well, I guess we could, the first thing it says is this 530 newtons. That's the free body diagram, by the way. There's no other forces, so sweet. All right, so the weight is 530 newtons. The goal is to figure out what is this force and what is this force. Okay, then let's continue. This says the diving board has a length of 3.9 meters. Nice. So we could draw that in. 3.9 meters. And the bolt is, it says the board has a negligible weight and is bolted down at the left end while being supported 1.4 meters away by a fulcrum. So that's this distance here to the fulcrum. Okay, 1.4 meters. So you could see like the numbers and the distances and the forces, they kind of all start piling each other up. So it's nice to draw a nice big diagram for yourself. So great, we have our diagram. Step 3, choose a convenient set of axes. And this one, it looks like they're all pointing straight up and down. So I would make that the y-axis like we typically would. And we could even draw it in if we want. We could make the x and the y-axes here. X, Y, just so that we show ourselves. I'll put it off to the side here because it's pretty straightforward. 4, apply the equations that specify the balances of the forces at equilibrium. So in the x direction, the net force is 0, and there's no forces in the x direction. Nothing's pointing to the left and the right. In the y direction, what do we have? We have the force of friction. See, I knew I was going to do that. We have the fulcrum force is pointing straight up, so I'll make that positive. And then the bolt force is pointing down in our diagram, and the weight is acting downward. Okay, cool. So, and we know that this is going to turn into 0, and we know that this is 530, but so far we have 2 unknowns and 1 equation, and that's not good. So we got to figure out another equation that we can use to help solve for this, for these unknowns. So we would use the torque, the net torque. All right. But before you could do that, you have to do step 5. It says select a convenient axis of rotation. And it could be anywhere along the board. Now you might say to yourself, well, it's rotating around this fulcrum, right? Doesn't it? That's what the point of the fulcrum is trying to rotate around that point. Yeah, you could definitely do that. That's fine. And especially because that's one of your unknowns and it would eliminate that unknown because the lever arm is 0. But just to illustrate a point here, let's make the axis over here because the point is it doesn't matter where we put the axis. The net torque is 0. You're in equilibrium. You're not actually rotating at all. It's in equilibrium. So the axis could be anywhere. And this is another unknown force. So the lever arm is going to be 0 because the distance between that line of action and the axis is 0. So that means this torque is going to go away. It's not going to be in our equation. But this one is. So we're going to have to figure out what that lever arm is and what the weight is. Okay. Another reason we would put this here, not only to illustrate a point, but look at these distances that they're giving us. Speaking of the lever arm, which would be the most convenient? It seems like everything is being measured with respect to this left side over here. So if we made this the axis instead, all right, we'd have to figure out what is the distance between the weight and this axis over here. Could we do it? For sure. 3.9 minus 1.4. Is that more work? Technically, yes. So let's make our lives a little bit easier and make the bolt the fulcrum. So the net torque is equal to the torque supply, and now you have to think positive, negative, right? So here's our axis. If the force is making you go, it looks like it's going this way for this force. So is that clockwise or counterclockwise? That is counterclockwise. So this is going to be a positive torque. And the weight is making you rotate this way about this axis, right? So that's clockwise. So that's going to be a negative torque. Just like we set it up before, the positive and the negative signs are going to come into play. This torque doesn't make you rotate, this force I should say, this doesn't make you rotate about that axis at all. The torque is 0, so that it's going to go away. It doesn't matter what that is. So we'll start with that one. It's good to work left to right. The net torque is equal to the torque supplied by the bolt, which we know is going to be equal to 0. Then I'm going to say plus the torque supplied by the fulcrum force, because it's going counterclockwise. So that's positive. Minus the torque supplied by the weight, because the weight is making you go clockwise about this axis that we picked. Okay? Now we can try to plug in some numbers here. We know the net torque is going to be 0 Newton meters. I'm going to take the point off for units. Really, you should write it on the side. Man, I got to write my units in. It's going to be a little bit confusing, but 0 Newton meters, okay? The torque is equal to the force times the lever arm. We learned that yesterday. This torque is the fulcrum force times the lever arm for the fulcrum. And then the weight torque is equal to the weight times the lever arm for the weight. I'm using my subscripts again to make sure we keep everything nice. All right. So 0 is equal to, well, this force, we don't know, but we know this lever arm is 0 meters. We know this force, actually, no, we don't know this force, but we know this lever arm is 1.4 meters. The line of action for this force is 1.4 meters perpendicularly from the axis. So that's going to be 1.4 minus the weight we said was 530 newtons. I do have that unit on the side there, right here, but I'll write it in. And the lever arm from the axis to that line of action is 3.9 meters. There's a lot to keep straight here, okay? This goes away, and you're left with 1.4 times the fulcrum force, and then the torque supplied by the weight is actually 2,067 Newton meters. That's this torque in the negative direction. Okay? Oh, sorry, I flipped that up there. So actually I subtracted this to that side, so that I was like, where's this negative? It's going to turn into a negative number, but it doesn't. So the way you solve that, it's up to you. The frictional force, I did it again. The fulcrum force is equal to 1,476.4286. We'll try to be nice and do sig fig. So 1,480 newtons. Okay. Nice. That's really good. So we know one of the forces, and what we can do is come back over here, or we could choose a different axis now, maybe this one over here. It doesn't matter, but let's use that net force in the y direction. We know that net force is equal to 0 newtons. We know the fulcrum force now is 1,480 minus FB minus 530 newtons. All right, and now look at that. One equation, one unknown. We know the force that the bolt is exerting is equal to 950 newtons. Man, man, oh man. So not only is there like a third equation that we have to, think about, but this is different from the other ones because now when you're doing the torque equation, you have to think of a convenient axis to use it. So that's kind of weird. You want to pick one that eliminates one of your unknown variables if there's two of them. So that's like a weird thing. And then how else do you pick the axis? Well, you want to look at what distances you have. Maybe one is easier than the other. So you want to try to pick where the axis is that all the distances are measured to if possible. And then you have to remember that the torque is equal to the force times the lever arm and do that correctly. And it's easy to get mixed up if the distances aren't as convenient as this one was, like is going to be in the next example. I'll do one more example. Plus, you have to remember that positive and negative, that's how we show the direction, and counterclockwise is positive and clockwise is negative. So there's a lot to keep track of with this. But I know you could do it. You're a smart, savvy physics student. So let's do the next example. Oh, before we do the next example, a note about the weight of the board, okay? It said it was a negligible weight. In this next example, it's not going to be. So it said if the board didn't have negligible weight, you'd have to add the weight of the board into your free body diagram. If it was a uniform board, you can assume that the weight acts in the center of the board, right here, and there would be another weight. So you would have the weight of the board and the weight of the diver, okay? And this is the center of gravity for the board. So let's try one out that looks like that. This one says a painter is above the first floor of a house on a scaffold, which weighs 500 newtons. So now, instead of like the diving board being negligible weight, the scaffold has a weight of 500 newtons. The scaffold is 4 meters wide and is supported by 2 ropes attached 0.5 meters in from each end. So the ropes are supporting it, and they're telling you a lot of information that'll help us with the lever arm. The painter has a mass of 70 kilograms, so we're going to have to figure out the weight of that painter, and stands 1 meter from the left side of the scaffold. Again, we're thinking about the lever arm here. Calculate the tension in each rope. So the rope are the things that are supporting it. The tension is the force along the rope. And there's 2 tensions here. So again, 2 unknowns. We definitely have to use our equations, at least 2 equations for those 2 unknowns. If you'd like, you could pause the video and try this out on your own. So the first step is to select the object that we're analyzing, and I'm going to analyze the scaffold itself. So then step 2 is draw a free body diagram. So the free body diagram is going to look like this. Here's our scaffold. All right, then they tell you a lot of different information here. So let's see, let's go in order. It weighs 500 newtons, and we said that you can make it the center of mass, and you assume it's a uniform object, which means that the center of mass would be right in the middle. So the weight of the scaffold is equal to 500 newtons. I'll try to do it color coordinated like I have been. The scaffold is 4 meters wide, so we could start writing in that information if we wanted to. This is 4 meters wide. Okay, good to know. And is supported by 2 ropes attached 0.5 meters in from each end. That means it looks something like this. The ropes are here. So we could call this like T1 for the tension 1, and this is T2. Okay. We could also draw in our distances here. So this is 0.5 meters in from each end. That's what this means here. Okay. The painter has a mass of 70 kilograms. So again, we're going to draw a weight somewhere, and stands 1 meter from the left side of the scaffold. So they're not right in the middle, because this thing is 4 meters wide and they're only 1 meter away. Further than 0.5 meters though, right? So then we got this weight. Now we're not really sure if that's going to be more or less, but I did this problem beforehand and I know that it's more. So the weight of the painter, we're not sure what it is yet, but we could figure it out. That would be a good thing to know, since we know what the kilograms, well, you know what the mass is. Okay, so let's try to do that first. That'll give us one of the forces, and then we're just looking for these 2 other ones. Okay, I think that's all the info. Oh, no, I need to write. So this is, okay, 1 meter. Start thinking about where a convenient axis would be for this. So I mean axis of rotation, but for the step 3, it says choose a convenient set of x and y axes. Again, all the forces are pointing in the vertical direction, so we could use just the standard x and y axes. Nice. Apply the equations that specify the balance of forces at equilibrium. So the net force in the x direction is equal to 0 newtons, because there's no forces in the x direction. The net force in the y direction is a little bit more interesting. Going upward, we got T1 plus T2. Going downward, we have minus WP minus WS. Okay, should we find the weight first? I mean, I'm just itching to find the weight first, to be honest. So let's do that on the side over here. The weight of the person is equal to the mass of the person times g. The weight of the person is equal to 70 kilograms times 9.8 meters per second squared, and you get 686 newtons. I told you that's, it's going to be larger than the weight of the scaffold, so 686. Sweet. So we know that. But again, one equation, one unknown, that's not going to help us. We're going to have to analyze the torque. So step 5 says select a convenient axis of rotation. And it doesn't really matter where. You don't have to pick the same one as me. But let's choose. We definitely want to choose an axis that goes through one of our unknown forces, because again, we want the torque of that force to be equal to 0. Doesn't matter. It's going to be confusing either way, because we got to have to figure out the lever arms for these 3 to this axis here. Okay, so that's my axis. Then we're going to set the sum of the torques equal to 0. Okay, so let's write our net torque equation. And we want to think, right, okay, this torque is 0. What direction is each one? Maybe you want to do that beforehand. Maybe you want to go a little bit like, okay, that's going to make me go that way around the axis. Clockwise is negative. Clockwise is negative. Counterclockwise is positive. Makes it a little bit easier maybe when you're writing your net torque equation. So the net torque is equal to, all right, you could technically not even write this one in here because it's not supplying a torque. We know that the lever arm is 0. So I'm not going to write that one in. I'll write it in. Now, I won't. I'll keep it simple. So now we have the torque provided by the weight of the person. So we'll call that the torque of the person. And that's going to be negative minus the torque of the scaffold plus the torque of T2. All right. The net torque is 0 Newton meters because you're in equilibrium. Torque is equal to the force times the lever arm. The force in this case is the weight of the person times the lever arm of the person. The torque of the scaffold is the weight of the scaffold times the lever arm of the scaffold. And the torque provided by the tension in the second rope is the tension in the second rope times the lever arm for the second rope. Okay, now even though we have some nice red numbers drawn on our diagram, we actually don't have any of the lever arms yet. So maybe we should use a dark red for the lever arm. The lever arm for this is 0, so nobody cares about you, okay? But the lever arm for WP is from the line of action to the axis. So that's this distance here, okay? Should I draw it like this? I guess that's going to get sloppy. All right, so that distance is 1 meter minus 0.5 meters. So this is 0.5 meters. Okay. For what is the lever arm for this one? Can you figure it out? Well, we said that this was the right in the middle. This is the center of gravity. So the whole thing is 4 meters long. That means this is 2 meters away from the end, but the axis is 0.5 meters from the end. So you have to do 2 minus 0.5. Tricky stuff. What the heck, Mr. Nangle? This is even hard to figure out, and it's only one of the many steps that we have to do. So that's the lever arm for the weight of the scaffold from the axis that we picked there, the green dot. That's the axis. So how far is it from this line of action Can you figure that one out? Try it on, think for yourself. I'm going to tell you the answer right now. Pause the video if you want. We're looking for this distance here. Okay? They're both 0.5 in from each end, and the whole thing is 4, so you've got to do 4 minus 0.5 minus 0.5. So did you say 3.5? You're wrong, but that's okay. I'd made the same mistake before. So this is 3 meters. So you got to think about it. You got to be very organized. All right. Look at these nice lever arms. See how they're all measured with respect to the axis? That's what we want. We don't want this mess. This is good information, but like we want some nice lever arms going on. Okay. That's like can be the trickiest part sometimes. Plus you have to remember the direction of everything. So minus the weight of the person times the lever arm for the person minus the weight of the scaffold times the lever arm for the scaffold plus the tension, which we're looking for, T2, times the lever arm for the tension, which is 3 meters. If you're super organized and you practice it, like you're gonna have to practice this, and you might get a question wrong every once in a while. Oh my gosh, that's okay. All right, that's how you learn, and then you get like I think is kind of organized, but I know as I do more, I'm gonna get even more and more organized. I see how like sloppy this is. Um, there's room for improvement. There's always going to be room for improvement. Speaking of, I just realized this video is already over a half hour long and I'm trying to make them like 20 minutes tops. Anyway, so the torque supplied by the person is 343 Newton meters in the negative direction. The torque supplied by the scaffold is 750 Newton meters in the negative clockwise direction. And the T2, you could do like 3 times T2 to help you solve, okay? So T2 turns into, now we know we could get one equation, one unknown. How satisfying is that? All the math nerds out there, like myself. 634.3 repeating newtons, okay? That's the force. That's the force. And it looks like T, oh, that's torque. No, that's tension. So that adds a whole other layer. You're going to write Newton meters here? No, the force, the tension is the force. So yeah, that's nice. Then we're going to take this force and plug it in over here. For this equation, we know the net force in the y direction is 0 newtons. T1 is now what we're looking for. T2 is 364. Really, we should just call it 364. The weight of the person is 500 newtons. And the weight of the scaffold. See, I made mistakes. People making mistakes. That's all right. I forgot my units. The weight of the person is actually 686 newtons. And the weight of the scaffold is 500 newtons. All right. Then you get T1, and it works out to be a positive number, which we're happy about, 821.7, 822 newtons. Wow, nice. When you get all the directions pointing the way they should, that's one good sign that you're doing things correctly. All right. Another good sign that you're doing things correctly is you feel good about yourself. Hopefully you watched this whole video, you learned something, and you're ready to tackle some interesting problems here. I know you could do it. Anyway, that's about it. Thanks for watching and have a great day.